All right, let's take a look at this check on galvanic cells and standard reduction potentials. So galvanic cell is a chemical system that spontaneously changes chemical energy to electrical energy using redox reactions. Sometimes you'll see these as voltaic cells as well. We generally tend to use the term galvanic, but you could see both. So what I've done is I've gone ahead and put up a diagram labeled for what one of these cells looks like kind of generically. So on the left hand side, I've drawn the oxidation. And so the oxidation half reaction is taking place on the left hand side, and then the reduction is occurring on the right hand side. And so a lot of times we'll see anox and red cat when it comes to these, so that you know that the oxidation is happening on the anode and the reduction is happening on the cathode, okay? And then Leogur or oil rig, whichever you want. So the generic one is showing that we have an anode, which is metal, and a cathode, which would be metal. And then we have these in solution. So we have a reducing agent on the left-hand side, that's going to be in this particular beaker, and then the oxidizing agent solution on the right-hand side. And what we see is that electrons are going to travel from the anode to the cathode. Now, we would start this process and it would very quickly stop if we didn't have some way of still transferring some additional charge values. And so we use something called a salt bridge. Okay, and so we have a solution that would be in the salt bridge, or sometimes it'll be kind of more of like a jelly type of a substance. Okay, sometimes we'll use in lab, we use a lot of times filter paper for us, but anyways, something that's going to allow us not to electrically stop in this process. And so we'll see the anion is going to travel towards the cathode, and the cation is going to travel towards the cathode. Anions towards the anode, cations towards the cathode. There we go. Okay, and so we want to be able to evaluate these and see. Now, they may not always be left versus right. Sometimes you might have to evaluate the data to determine which one will go where. So cell potential is the potential for electrons to travel in an electrochemical system. Electromotive force is another way that you'll see this sometimes. But the flow of electrons is spontaneous in a galvanic cell. And so they're going to flow from an anode to the cathode because the cathode has lower potential energy than the anode. And so we're going to be traveling towards the lowest potential energy of the system. We measure this in volts, capital V, and 1 joule of work per coulomb of charge. So we get a joule coulomb. They're equivalent to one another. And so we have these standard reduction potentials, and they are compared to the standard hydrogen electrode at 1 atmosphere of pressure and 1 molar of solution. And so we have a table for this, and I'm going to just switch you over to the table just really quickly. It's in the back of the book, and it's also in OneNote. And so here we see that standard reduction potentials. Now you need to know that on this is for the reduction of each one of these things. And so you'll see that the electrons are actually on the left-hand side. Okay, because if they're going to gain electrons, they're going to be being reduced. And so we know that we're going to have an oxidation reaction and we're going to have a reduction reaction, but all of these are listed as the reduction. So that means we need to be able to evaluate those. So the more positive reduction, so the E prime reduction, okay, that's those reduction potentials. So the more positive that value is going to go to the cathode, and the more negative is going to go to the anode. And so that is a really, really important thing to know as you are working through these. There's a couple different ways that we can look at a problem, and I hope I don't confuse you in the way that I'll explain that. So oxidizing and reducing agents, remember, the more negative, the stronger the reducing agent, and the more positive, the reduction potential, the stronger the oxidizing agent. So we have to think about all of that terminology again. There's some additional information on line notation on page 847 in your text. Take a look at that. It's just a different way that we can write how these look. Okay, so let's go down and take a look at how we could determine the electromotive force or the cell potential of a given cell. And so there's a couple different ways we can do this. One is we can write them out. And the other way is to just look at the reduction potentials for them. So if we're looking for the overall cell potential for an electrochemical cell, for a galvanic cell or anything that we're comparing these for, it's going to be the reduction potential of the cathode minus the reduction potential of the anode. Okay. Now, that is taking those numbers directly off the chart. So when you take them directly off the chart, then you're going to be able to use them in this particular equation. Sometimes when we evaluate these, we can do something where we'll flip them and we'll have one be represent the oxidation value and one represent the reduction value. So you can choose the one that you like best, and if you have questions about that, let me know so I can help you kind of navigate through that. Okay, so let's take a look at this first problem. So it says diagram the galvanic cells or cell, write the overall balanced equation and determine the cell potential for the following. So we have this reaction that's going to be occurring and we want to know how to take a look at this. So let's split this into half reactions. Okay. We see that zinc is on the left-hand side. So we're going to have our Zn, and then on the right-hand side we have the zinc ion. Okay. And then our other one is going to be our silver ion, Ag+. And then silver's on the other side, Ag solid. Okay, and so we have to add our one electron here. All right, so what we want to do is we want to find out what the values for this. Now, we see that the bottom one is gaining electrons, so that's a reduction. Okay. And if we go back up, we know that the reduction is a red cat. That's going to be at our cathode. So this is going to be the reduction. Okay. And so we're going to kind of keep that in mind here in just a moment. And then the other one is actually the oxidation. So if we're just going to use these two values, we can say, okay, well, we know that the reduction is happening at the cathode, and we know the oxidation is happening at the anode, and we could plug those values straight from the chart into this particular equation, okay? So the other way that we can do that is to actually flip the sign of one of these as well. So let's go ahead and go back into that chart just so we can take a look. So now I have to find them. I didn't find them ahead of time. Here we go. Here's the silver. Okay. And that looks just like how we have it. This is actually the reduction. So 0.80 volts is going to be our reduction for that. And then for zinc, let me see if I can find zinc on here. Here we go. Now, zinc is negative 0.76. Great. That is in the reduction. So if we're going to apply it towards the oxidation, we have to make that a positive sign. If we flip the equation, we have to flip the sign for the voltage. So let's now go back in here. And so our E value for that was 0.76 when it was in the oxidation portion. And then for the other one, we said that was 0.80. Okay, now if we were actually going to apply it like we see in the equation up above, what we would see is we would keep both of the reduction, okay, because this was actually the oxidation, and this one was the reduction. So if I wanted to keep both of them, then what I would do is I would say, okay, my E cell overall is going to be equal to the reduction at the cathode, so 0.80 minus, and this value when it was being reduced, remember, was 0.76, a negative 0.76. Okay, and so when we do that, then we get 1.56 volts. Okay, so that is using this equation to get that. Now, the other way that we can do it is we can flip that around as the oxidation, which to me I almost like better just because I'm really having to conceptualize it, but you can do this either way. So now if we look at these, we know that we have to multiply the bottom one, we have to have 2, so we're going to multiply this by 2, so we have 2 electrons in both, and the electrons cancel out. That does not cause us to multiply the 0.8 times 2, though. We don't do that in this particular situation. That's not a convention that we use here. So then we end up with zinc plus 2Ag plus ions forms Zn2 plus 2 Ags, okay? And then we can add these up. So now we're gonna, if we do it this way, if we have the oxidation value and we have the reduction value, we can just add those up. And so for the overall cell, if we add those up, we still get 1.56 volts. Okay, you can do that either way. Okay, you can do it either way. So it's really up to you on how you do that. Okay, so we said that the oxidation, so we have to then diagram this. So the oxidation half reaction is going to be at the anode and the reduction is going to be at the cathode. Okay, so when we do that, I'm going to go ahead and go, this is anode, anox. Okay, so this is our oxidation half reaction, which means the other side is going to be our cathode, which is going to be our reduction. I don't generally tend to write them this way, but if you were asked to evaluate one, don't just assume that the left is the anode and the right is the cathode. You need to actually take a look at what you have there. Okay, so let's apply this. So that means that our anode is going to be the zinc metal. Okay, so if you have the metal is going to be the actual anode. And that means our solution that would have zinc ions in it, Zn2 plus, is going to be in the solution itself. Okay. On the other side, we're going to see that the silver metal is going to be the actual cathode, okay. And then the silver ions is going to be in solution. Okay. We also need to make sure that we have that salt bridge. So here's our salt bridge. Oftentimes we are asked which directions things go, so remember that the anion is going to go towards the anode solution, okay, and the cation is going to go towards the cathode solution. So then the question becomes, which direction are our electrons traveling? Our electrons always travel from the anode to the cathode, from the oxidation half reaction to the reduction half reaction. And so we know that our electrons are traveling this direction. Okay. All right, let's take a look at another one of these. Now this is nice because they've given us all of our values. So it says diagram the galvanic cell, write the overall balanced equation, and determine the overall cell potential considering the following information. Now, with this, we have to know, okay, both of these are the reductions. Which one of them is going to actually be, are we going to have to flip to show the oxidation? So let's go back up in our notes here. And you see this more positive reduction potential is going to be our cathode. Okay. And the more negative is going to be our anode. So which one would be more positive? It's going to be the larger value. We don't have a negative value in this case. And so this one here is going to be the more positive one, okay? And the one on the bottom is going to be the more negative. And so this is the one we have to flip around because it's going to be the anode. So I'm just going to mark this one here. This is the more negative. So if you don't have one that's a negative number, then it's just going to be the smaller value. So the reduction, so for the more negative value, that is going to be the anode. And remember, at the anode is where oxidation occurs. So we're going to flip this whole thing. Okay. So flip the whole thing. So 2Br minus and then Br2 plus 2 electrons. And when we flip our overall equation, we're also going to flip the sign. So that means our new value is going to be negative 1.09 volts. Okay, I'm actually going to move that over just a little bit to line things up. All right, there we go. I like it there better. Okay, now that we've done that, we can go ahead and add our equations together. We do have 2 electrons on each side, so we don't need to worry about changing that. Okay. And so we have Cl2 plus 2 Br minus. Of course, those electrons are going to cancel each other. Go to 2Cl minus plus Br2. Okay, now we have to add up these values. So we're going to take for the total cell potential, we're going to take the 1.36 plus the negative 1.09. That's again in volts. And we get 0.27 volts. Okay. Now, this is an interesting situation. So in the last one, we said, okay, look, our zinc that's a metal and our silver that's a metal are going to be the anode and the cathode. In this particular case, these are actually gases. Okay, so Cl2 is a gas. This is a gas, and this is a gas. Okay, those are diatomic molecules that are gases. And so, actually, no, that's not the case. Br2 is a liquid, excuse me. So if we do not have metals, or if one of them is not a metal, what do we do? Okay, so the question is no metal, no problem. Okay, so the anode, and in this case, and it doesn't always have to be both of them, and the cathode must be a non-reactive or unreactive or low reactive metal. Usually the go-to on this is going to be platinum. Okay, PT. Okay, so that means let's put our platinum as our anode and cathode. Okay. We know that our oxidation is the one that we had to flip, right? Because it's no longer being in the reduction state. So that means that this one here with bromine was our oxidation. Okay. And so for the half reaction for the oxidation, okay, so the anode again is oxidation. Br2 is a liquid, and we're going to have those bromine ions in there as well. The other half of this was the reduction. Okay, the reduction is occurring at the cathode. Now, we know that the chlorine ions are going to be in solution. How do we get the gas in? And this is kind of an interesting situation. So with this gas, we actually have to bubble in. Let's see if I can do this. Let's try that again. Okay. We have to bubble in some chlorine gas into the solution. So that Cl2 gas has to be bubbled in to the solution. So we're going to have some little bubbles that are going to go in there. Okay, again, we need to have our salt bridge. Let's go ahead and label that. Okay, our anions are going to go to the anode side. Our cations are going to go to the cathode side. And then the final question, which direction do the electrons travel? Of course, they are going to go from the anode to the cathode. So our electrons are traveling this direction.